Okay, let us do the same thing, follow the same steps for another variable, namely temperature. Two objectives of this: certainly emphasize that, specifically emphasize that the material derivative can be applied for any property. We are done first for velocity, it can be done for temperature, can be done for concentration. Okay. Now, that is why all whatever we are discussing are all discussed under the heading called fundamental concepts. They are not necessarily related to fluid flow, though a fluid mechanics book discusses all these concepts. These concepts are applicable for fluid flow, energy, heat flow, and then later on species flow also. To emphasize that also, here I am illustrating the substantial derivative of temperature. Okay. Let us take an example. What do we mean by substantial derivative of temperature? What you hear is a here is a household geyser. Water flows in, gets heated and then comes out. Now, you have a particle here. What is the meaning of substantial derivative? Rate of change of property of a fluid particle, okay. In this case rate of change of temperature. So, as you follow the fluid particle, what is the rate of change of its temperature is the substantial derivative dt by dt. Okay. Now, take example of temperature, and what we are interested is dt particle by dt. Just like we had velocity earlier, we have T of temperature particle here, and just like we wrote earlier, at any instant at any particular location along the path of the particle, we said velocity is equal to the velocity field, velocity of the particle is equal to the velocity field. Similarly, here the temperature of the fluid particle, or more specifically temperature sensed by the fluid particle, should be equal to the local value of temperature field. Okay. So, once again relating Lagrangian quantity to a Eulerian quantity. Okay. Now, so the T particle in the time derivative is replaced in terms of the Eulerian temperature T, and so total derivative, once again we differentiate partially with respect to the 4 independent variables x particle, y particle, z particle and time, and then so now this derivative, this special derivative is called the substantial derivative dt by dt. So, we have dou t by dou t here, this becomes 1, and as we have done earlier, we have represented this by the x component of velocity field. X particle has been replaced with x, similarly y direction, z direction, and this is called substantial derivative of temperature. I can't use it over acceleration, that is applicable certainly for velocity only. We call this only as substantial derivative of temperature. Okay. So, now to little bit imagine about this. We said we follow the fluid particle, something like sitting on the fluid particle. Okay. You would have seen in some movies a person becomes like a fly and then gets into a house and so on. So, likewise imagine yourself as something like a temperature resistant ant, get into it, and then you start the stopwatch, and then what is the rate of change of temperature you would measure, and that is dt by dt. Okay. That is how you can imagine that. Okay. So, now we will extend this to any variable. Okay. Throughout the course you will come across substantial derivative of course velocity, you will come across density, you will come across temperature, concentration, I think you will come across pressure as well. So, and so substantial derivative all are the same physical significance, rate of change of property as you follow the fluid particle. Now, of course, this x component of the velocity dvx by dt and substantial derivative of x component of velocity. Okay. Now, this combination of terms can be represented in terms of vector notation. Okay. Just to slightly introduce you to vector notation, so that the expression become very simple and elegant. Okay. Now, we know the velocity field is a vector field, and it has 3 components Vx, Vy and Vz, and we are familiar from calculus the gradient operator, which is dou by dou x I, dou by dou y j and dou by dou z k. So, now if you take a dot product of these two v dot del, then you will get these three terms. So, I dot I becomes 1. So, we have V x dou by dou x here, dou V x by dou x, of course operating on x, and V y, and this term gives you V y dou V by dou y, similarly the next term. Okay. So, this set of terms can be represented very nicely in terms of V dot the gradient operator. Okay. Now, in this particular case we have dou by dou t and then V x here, and then all these terms without the V x is represented by V dot del, and then to be more formally we say operating on x, V x. Similarly, we can write for the substantial derivative of temperature, which you have seen, okay, dou t by dou t and then all other terms. We will shortly see the significance of each of these terms, and once again this can be put in terms of the V vector and the gradient vector. Okay. This dou by dou t plus V dot gradient is called the substantial material derivative. Okay. So, what it does is expresses in terms of the vector notation. So, either we can use d by dt in terms of vector notation or the expanded form. It is better to know both the equivalent forms of the same expression. As I told you, we can represent substantial derivative for any variable, for example, as shown here for concentration. Okay. So, just to repeat, it says rate of change of a property, it could be velocity, temperature, and then concentration, okay, of a fluid particle, and that is a Lagrangian time derivative, Okay. The left hand side is Lagrangian time derivative. Most importantly, we are expressing that in terms of Eulerian or field variables. That is the most significant importance of substantial derivative. Right hand side is the Eulerian field, concentration field, temperature field, velocity field, etc. Okay. And if you use the derivatives in this particular combination, okay, dou by dou t V dot del operating on any variable, the physical significance what you get becomes Lagrangian. Okay. That is a significant advantage. Okay. If you measure a property in terms of Eulerian variables, you can get the Lagrangian derivative meaning. Okay. Now, and that is what I just explained to you. Knowing the velocity and temperature field, accordingly concentration field or any other field, which is Eulerian description, rate of change of temperature following a fluid particle, which is the Lagrangian description, can be obtained. Okay. Okay, what is the physical significance of this material derivative? What do I mean by that? We have seen the significance, of course, it has two components in it, two parts in it. Let us see what are the meaning of those two components. Okay. Now, once again we will start with temperature in the present case, so that easy to understand, and then go to velocity. Okay. Now, this is written in terms of the velocity vector and the gradient vector. I have expanded that and written here in terms of the full expression, so that you can slowly get familiar to both the vectorial representation and the full representation. Now, there are two components to it. First is called the local component. Why is it a local component? As I told you, remember when we derived it, when we took the derivative, we kept the x, y, z constant. So, it is a particular location. So, this tells what is the rate of change of temperature at a particular location. how can it happen? Because of fluctuation in temperature, change in temperature. This particular room, let us say if you are following a fluid particle, the particle is at a particular location, the temperature field has some fluctuation for whatever reason, it goes from one value to other value, it fluctuates, there is some transient in that, some unsteady state in that, steady stateness in that. So, the particle is at a particular location, experiences a change of temperature because of the unsteadiness of the temperature field. Okay. So, the first, the local component, due to the unsteadiness of the property, in this particular case temperature. What is the next what is the significance of the next component? It is called the convective component. Why is it happening? Two contributions are there. First one, there should be two conditions for that to be non-zero. What is that? First of all, we have dou t by dou x, dou t by dou y, dou t by dou z. What do they represent? Change of temperature with respect to spatial coordinates, x direction, y direction, z direction, etc. So, now which means that there should be a spatial variation of the property. If there is no spatial variation, these terms will become 0 and second term will not contribute. So, first requirement is that there should be a spatial variation. Secondly, there should be fluid flow, only then Vx, Vy, Vz will be non-zero, only then you will have non-zero value. So, for the convective components represents the contribution to the substantial derivative due to spatial variation of the property and motion of the fluid. If either of them is absent, that term will be 0 and it will not contribute to the derivative experienced by the fluid particle. So, in this case, as the fluid particle flows through this heater, it can have two components. One, at a position particle experiences change in temperature, as it moves from one location to the other, it experiences change in temperature because of the spatial variation. Okay. And we can talk about movement only when there is flow. Okay. So, time rate of change of temperature of a fluid particle as it moves through the temperature field. And given velocity and temperature field, what is required? You require this velocity, you require the temperature field. Okay. What is the temperature field? T as a function of x, y, z and time of course. Okay. So, given velocity and temperature field, Euler description, you can find out the rate of change of temperature experienced by a fluid particle as it flows, the Lagrangian description. Okay. We will just extend this to the velocity. We have written the expression for the acceleration of fluid particle in the x direction, which is this dvx by dt, this in terms of the vector notation, and then we can expand this same in terms of the components. This is of course more easily understandable compared to this, but this more compact notation compared to this expression. Okay. So, easy to begin with, we will use this, and then when you get practice you can start using this expression. Okay. Now, because it is velocity, because it is derivative velocity, this has a name other than our substantial derivative velocity. This is called the total acceleration, this is the local acceleration, and this all terms put together represents the convective acceleration. If we have temperature, concentration, pressure, any other variable, we just call it as substantial derivative, local component and then convective component. Because it is velocity, we call this the total acceleration, local acceleration and then convective acceleration. Okay. Physical significance, all are analogous. Okay. So, two components as we have seen earlier, two components of the material derivative. One is the local component, because once again because it is velocity, it is local acceleration. So, at a particular position the particle experiences change of velocity with respect to time, some fluctuation velocity, okay, due to the unsteadiness of the property, in this case the x component of velocity. Second one is the convective acceleration, as it moves from one place to other place there is change in velocity. Okay. This example, okay, from one place to other we have seen it will experience increase in velocity. Okay. So, due to spatial variation of the property, in this case velocity, and motion of the fluid. Okay. And physical significance we have seen earlier, time rate of change of velocity of a fluid particle, and as it moves through the velocity field, and in this case of course in the earlier case we require the velocity field and the temperature field. In this case just of course only velocity field. If you know the velocity field, then you know this v x, v y, v z. If you know the velocity field, you know all the derivatives. So only velocity field is required here. So given velocity field, find rate of change of velocity experienced by a fluid particle as it flows through the domain, and that is a Lagrangian description. Okay. So let us take some examples where the two different terms only contribute. Okay. The first example, first two examples are the case where only the local component contributes. Okay. So what I have shown here is a cup of coffee. You can also imagine a cup of tea. Tea is supposed to be more healthier than coffee, that is what I came to know. So the substantial derivative of temperature, what does that mean? As usual, so imagine a particle there in the fluid particle in the cup of coffee, and even if you blow air to cool it, there is not much motion of that, there is no fluid motion. So because there is no fluid motion, this Vx, Vy, Vz are all 0. There could be there will be temperature variations, maybe it is slightly colder here, warmer here, there will be temperature variation, but there is no velocity component. So this term will not contribute, but as the coffee is getting cooled, if the particle is at a particular location, it experiences the rate of decrease in temperature, and that is why the rate of change of temperature experienced with the particle has only one component because of the unsteadiness. Sometime back we discussed unsteadiness, it is an example for unsteadiness of the temperature field. The temperature field, which is the temperature of the coffee, reduces. So the temperature has a unsteady component in it. There could be spatial variation also, because there is hardly any flow, this term will not contribute. As I told you, it requires two conditions, there should be a flow, there should be a gradient. One of them is not here, so only the local component plays a role here. Okay, let us take another example from fluid flow. What you have here is a pipe of constant cross section, okay, so that there are no velocity gradients. We want to consider a case where only the first component contributes, that is why taken a case where the pipe of constant cross section throughout. Okay. So that is why the velocity distribution shown here, there is no, it is all same. Okay. Now, but the velocity can be a function of time, okay. The V naught whatever can be a function of time, let us say vary sinusoidally or some fluctuations are there. So what happens in this particular case, this will contribute at a, if you are looking at a play, if you are at a particular location or the particle is a particular location, it experiences a change in velocity with respect to time. But now as you follow the fluid particle from one place to the other, there is a flow, this term is present, this term, these of course in this case only one component is present, but otherwise these velocity components are present, but there is no gradient in the velocity. Okay. This is a case where second term does not contribute because the gradient in the velocity is not present, that is why he specifically took a case where the pipe has a constant cross sectional area. Though there is flow, but there is these terms are not present in this case, they just become 0, and once again the acceleration experienced by a fluid particle has only one contribution from the local component, local acceleration. The total acceleration becomes equal to the local acceleration. Okay. Let us take another set of examples where we have contribution from only the convective component. Okay. What is that example? The household example, the geyser example which I discussed some time back. Usually this operates under steady state condition. You have a constant inflow, constant outflow, and let us say water enters at some 30 degrees, leaves at some 70 degrees centigrade. So, all these conditions are all same. So, if you are at a particular location, the particle is at a particular location, the temperature field has no unsteadiness in it, it is just a steady state and steady state field. So, this term will not be present, and that is what we actually mean by steady state. When we mean steady state, at a particular location there should not be any change of a property, in this particular case temperature. Now, what happens as there is certainly flow through this medium. So, Vx components are present, it could be one dimensional or multi-dimensional, and then there is gradient also along the path of the fluid particle. There is increase in temperature as the fluid flows through this. So, from one location to the other, the fluid experiences a change in temperature. Why does it experience? Because the temperature varies along the path. So, the convective component contributes and the local component does not contribute. So, the variation in temperature experienced by a fluid particle has only the convective component. In this particular case, there is a gradient and flow of velocity, and the velocity flow is also present. Now, let us take another case where we have taken flow through a channel, but in this case we have specifically allowed for variation in the cross sectional area, and you have a larger cross section area, a smaller cross section, once again it expands and the cross section area increases. So, here you have a from here to here there is increase in velocity, and then once again the velocity goes back to the original value. So, we have considered a case where there is spatial variation of velocity, and now unlike the earlier case we are just considering a steady velocity field, the velocity does not change with respect to time. So, this term does not contribute. Now, these terms contribute, of course there is flow. So, Vx, Vy, Vz could be there, in this particular case only one component is present, and then there is spatial variation also. So, these terms contribute. So, the acceleration experienced by a fluid particle is only because of the convective component. The total acceleration becomes equal to the convective acceleration. In these particular these examples, if you are at a particular location, there is no change in the property, no rate of change of that property with respect to time. If you put an instrument here, it will not show any change in velocity. If you put an instrument here, it will not show any change in temperature. But if you travel along, and then along this, then you will experience a change in temperature velocity. Okay.